In this video, we're going to be working on some problems, some exercises that use the theory that we picked up in our last video about random variables. So let's just jump right into this. Our first problem, we have an insurance company that pays $10,000 if you die that year, $5,000 if you're disabled, or $0 if neither occurs. So basically this is an insurance policy that pays $10,000 for death and $5,000 for disability. And it says, suppose that the death rate in any year is 1 out of every 1,000 people, and then another 2 out of every 1,000 people suffer some kind of disability. We can display the probability model for this insurance policy in a table like this. So here we put our table, here's the payout, probability of that happening, and then in the event of death, disability, or neither. Okay? So we learned that the payout for death is $10,000. The payout for disability is $5,000. And the payout for neither is 0. Okay? If you have a good year, you don't cash in on your insurance. The probability of dying in a particular year said 1 out of every 1,000, so that's going to be 0.001. Probability of disability is 2 out of 1,000, so that's 0.002. And therefore the probability of neither one happening would be 0.997. So the question is, if we insure exactly 1,000 people, what is the expected value of the total payout for the year? Well, think about it. If we insure 1,000 people, we're going to expect 1 person to die and 2 persons to become disabled from the rates that we were given. So I'd say that my expected payout is going to be $10,000 plus 2 times $5,000, and that's $20,000. Okay? And the next question asks, what is the payout per policy? Well, if I've insured 1,000 people and I'm expecting to pay out $20,000, that would be $20 per policy. Okay? Now there's another way that we could have done this, and this is the more common way of finding the expected value of the policy, and that is to make another column here where we multiply x times px, and we say 10,000 times 1 over 1,000 is 10, and 5,000 times 2 over 1,000 is 10, and 0 times anything is 0, and when we add these up, we get 20. This is the method I use to always find the mean of a random variable, and that's exactly what we're finding here, the mean of this random variable. Okay? And then finally the last question says, if we charge a $50 premium for a policy, a premium is merely the price they charge for the policy. How much money would we expect to make? Well, I think we would expect to make 50 minus 20, which would be $30 per policy. Okay? We would be bringing in $50,000, and we would expect to pay out $20,000, so that sounds like $30,000 to me, which is $30 per policy. Alright? Let's look at our next problem. Next problem has to do with car repairs. Okay? We have that Buck took his minivan in for repair recently because the air conditioner was cutting out intermittently. The mechanic identified the problem as dirt in the control unit and said that in about 75% of such cases, drawing down and then recharging the coolant a couple of times cleans up the problem and costs only $60. If that fails, then the control unit must be replaced at an additional cost of $100 for parts and $40 for labor. Okay? So the first question is, define the random variable and construct the probability model. Okay? My random variable is x is the cost. Okay? The cost of fixing this problem. Okay? And so I'm going to say, I'm going to make a little table here, x and the probability of x. It looks like x might take the values of 60 or 60 plus 140. So it's either going to be 60 or it's going to be 200. And according to our problem here, it says that there's a 0.75 probability of it being $60, which means there must be a 25% chance of it costing $200. Alright? This is our random variable. Here is our probability model. That's all you need for the probability model. You need to show the possible outcomes, every possible outcome, and the probabilities associated with those possible outcomes. And the probabilities should add up to 1. Okay? If they don't add up to 1, something wrong is happening here. So what is the expected value of the cost of the repair? Well, let's do the same thing we did last time. Let's create a column that says x times the probability of x. And 60 times 0.75 gets me 45. And 200 times 0.25 gets me 50. And when we add those up, I get $90. So what that means is the expected value of the cost of this repair is 90 bucks. Now, next question asks, what does this mean in context? Well, let me first tell you what it doesn't mean. It doesn't mean that I actually expect to pay $90 to repair the car. No. I'm either going to pay $60 or $200. 90 is not one of my choices. What the expected value means is, if this happened over and over and over and over and over and over, well, then I would expect the average of the next several times to come out to $90. Okay? Sometimes it's going to be 200, sometimes it's going to be 60. The average of those will come out to be 90. You'll notice it's closer to 60 than it is to 200. That's because 60 is more likely. Alright? So that's what that means in context. Not that I actually expect to pay $90, but that I would expect to pay an average of $90 if this were to happen over the long haul. More repairs. Okay? Here we have a probability model that describes the number of repair calls that Comcast may receive during an hour. Okay? So, you know something? I really prefer doing this in a vertical table rather than a horizontal table. So I'm going to change this, and I'm going to make X is going to be my repair calls. So X can be 0, or 1, or 2, or 3, or 4. And the probability of X, the probability of having 0 calls is 10%. Probability of having 1 call is 30%. Probability of having 2 calls is 40%. 10% chance of having 3 calls. 10% chance of having 4 calls. Okay? To find the expected value, again, X times the probability of X. 0 times anything is 0. 1 times 0.3 is 0.3. Just a second. Okay. 2 times 0.4 is 0.8. 3 times 0.1 is 0.3. 4 times 0.1 is 0.4. And when I add all these up, that comes out to 1.8. Okay? That is the number of calls that Comcast should expect per hour. So I would call this the expected value of X, or I can also call it mu, and that is 1.8 calls. Are they going to get 1.8 calls in the next hour? No, you can't get a fractional call. Okay? That's not one of the choices. Again, what this means is, over the next several hours, I'm expecting that to average to be 1.8 calls per hour. Okay? Now to find the standard deviation. Okay? Well, what we have to do is, we have to find the difference between each of these x's and our mean. Our mean being 1.8. So 0 minus 1.8 is negative 1.8. 1 minus 1.8 is negative 0.8. 2 minus 1.8 is 0.2. 3 minus 1.8 is 1.2. And 4 minus 1.8 is 2.2. And so now what I'm going to do is I'm going to square these values. X minus mu squared. And let's see, 1.8 squared is 3.24. 0.8 squared is 0.64. 0.2 squared is 0.04. 1.2 squared is 1.44. And 2.2 squared is 4.84. And now the last thing that we do to find the standard deviation, actually there's two more steps, but the last one's very, very quick. The last thing we do to find the variance is we multiply these squared differences times the probability of that occurring. So it's x minus mu squared times the probability of x occurring. And 0.1 times 3.24 is 0.324. 0.3 times 64 is 0.192. 0.4 times 0.04 is 0.016. 0.1 times 1.44 is 0.144. And 0.1 times 4.84 is 0.484. Adding all these up, I believe I get 1.16. And that is my variance. Okay? So the variance is 1.16. But that's not what it asks for. It asks for the standard deviation. How do we calculate standard deviation? It's the square root of the variance. So the standard deviation is the square root of 1.16, and I get that to be about 1.077. Okay? All right, let me show you a trick. I don't recommend doing problems like this, but here's a pretty easy way to check and make sure you did it right. Take your TI-84 or TI-83, click on Stat, Edit, okay, and I'm going to get my list here. Let me clear out this list. And what I'm going to do is, I've noticed that all of my probabilities are in tenths. So what I can do is I can make a data set that has 1 0, 3 1s, 4 2s, 1 3, and 1 4. Okay? So it has all of my repair calls with their probabilities. Okay? So I'm going to have 0, 1, 1, 1, 2, 2, 2, 2, 3, and 4. Okay? So 10% of my numbers are 0, 30% of my numbers are 1s, 40% of my numbers are 2s, 10% of my numbers are 3s, and 10% of my numbers are 4s. And so now what I can do is I can just go to Stat, Calc, one variable stats, and I see that the mean is 1.8, just like I got 1.8 there. And the standard deviation, sigma, not S, but sigma, is 1.077, just like I got right there. So, well, call me a cheater if you want to, but I think it works pretty well. Next problem. Okay, this is actually straight out of the textbook. Given independent random variables with means and standard deviations as shown, find the mean and standard deviation of each of these variables. Okay? Well, let's just charge right into these. The expected value of 0.8 times y. Expected values are really easy. Okay? This is just 0.8 times the expected value of y. Okay? Anytime you have the expected value of a constant times a random variable, it's just the constant times the expected value. So it's just 0.8 times the mean of y, which is 240. It's 0.8 times 300. Okay? The standard deviation of 0.8 times y is, hey, the exact same thing. 0.8 times the standard deviation of y, which is 0.8 times 16, and I believe that comes out to 12.8. Correct me if I'm wrong. Oh, I'm sorry, you can't do that. You're not here. But yeah, that's right. Okay? So, just a constant times a random variable, that's easy. Now, on the next one, we have 2x minus 100. We have a constant times a random variable minus a constant. Okay? So the expected value of 2x minus 100 is going to be 2 times the expected value of x minus 100. So that's easy. 2 times 120 minus 100. 2 times 120 is 240, minus 100 is 40. So, hey, no it's not. 2 times 120 is 240, minus 100 is 140. So let's put a 1 there. Okay? The standard deviation of 2x minus 100 is just 2 times the standard deviation of x. Okay? This thing doesn't do anything at all. So let's talk about this just for a second. Okay? We have 2 times x minus 100. So let's look at x. X is a random variable. Think of it as there's a PDF, a data set that corresponds to this random variable. So what you do is you multiply everything by 2, so it gets bigger. Then you subtract 100, so it shifts down this way. Okay, when it got bigger, it got more spread out as well. It got twice as spread out as it was before. When it shifted down by 100, that didn't change the spread at all. So the 2 does affect your standard deviation. The 100 doesn't. So that's why we do the standard deviation of 2x minus 100 is just 2 times the standard deviation. The 100 doesn't matter at all. Alright, so that means this is going to be 2 times 12, which is 24. Alright, now we look at x plus 2y. The expected value of x plus 2y. Again, means, expected values, these are easy. It's just the expected value of x plus 2 times the expected value of y. And that's 120 plus 2 times 300, and that's 720. Okay? Piece of cake there, no problem. Now for the standard deviation. What I'm going to do is I'm going to go up here and I'm going to make a new column and I'm going to call it variance. Okay? The variance of x is 144. The variance of y is 256. Where did I get these numbers? Because it's the standard deviation squared. That's what the variance is. Okay? So the variance of x plus 2y is the variance of x plus the variance of 2y. And the variance of 2y is 4 times the variance of y. Why? Because you take this 2 and you square it. Remember, the variance, it's the average of squared differences. So that means if you multiply everything by 2, the variance is going to be multiplied by 4. So now we add up these variances and you get the variance of x, which is 144, plus 4 times the variance of y. That's 4 times 256. And that comes out to 1,168. That's my variance. How do I calculate the standard deviation? Standard deviation is the square root of the variance. So standard deviation is going to be approximately 34.176. Okay? D, 3x minus y. This is real similar to the last one. We have 2 random variables again, so 3x minus y. That's going to be 3 times the expected value of x minus the expected value of y. Like I said, means are really easy. And so that's going to be 3 times 120 minus 300. And that's 360 minus 300, which equals 60. Okay? Again, don't look at the standard deviation. Look at the variance. Variance of 3x minus y is going to be the variance of 3x plus the variance of y. You never subtract variances. Never, ever. Okay? That's just the rule of variances. If you're adding random variables, you add the variances. If you're subtracting random variables, you add the variances. You always add the variances. So this is going to be 9 times the variance of x plus the variance of y. And that comes out to 9 times 144 plus 256, which is 1,552. So what's the standard deviation? It's the square root of the variance. So the standard deviation is the square root of 1,552, which is approximately, I'm getting 39 about 39.4. All right? Let me scoot this up. And my last problem that I have here is y1 plus y2. Well, the mean, have I mentioned yet that means are easy? The mean is just going to be the mean of y plus the mean of y. So 2 times the mean of y. 600. Okay? The variance, well in this case the variance is kind of easy too. It's just the variance of y plus the variance of y. And that equals 256 plus 256, which is 512. The standard deviation, have I mentioned yet that the standard deviation is the square root of the variance? Because it is. It's the square root of 512, and that's approximately equal to 22.63. And there we go. Okay? Let's go to the next problem. A casino knows that people play the slot machine in hopes of hitting the jackpot, but that most of them lose their dollar. Suppose a certain machine pays out an average of 92 cents with a standard deviation of $120. So, if you play 5 times, what are the mean and standard deviation of the casino's profit? Okay, well let's see. First off, the machine pays out an average of 92 cents. So I'm going to have x be the payout. Okay? And so the expected value of x is 0.92. And the standard deviation of x is 120. Okay? So that's the payout. Okay? Now we need to look at the profit. So the expected value of the profit, well, the profit would be $1 minus the payout, right? So it's $1 minus x. Okay? Well, that's just going to be 1 minus the expected value of x, and that equals 1 minus 0.92, which is 0.08. So 0.08 is our expected profit per time that you play. Okay? And the standard deviation of 1 minus x is going to be all right, again, think about this. The 1, that doesn't matter. Because think of this as 1 plus negative x. And remember, when you add something to a random variable, that doesn't change the standard deviation. Now let's think about the standard deviation of negative x. All right, so you've got x, this random variable, right? And it represents some data. What's negative x going to look like? It's just that data turned around. Okay? It's that data flipped over the y-axis. Is the spread any different? No, it's a mirror image. So the standard deviation is exactly the same. So what that tells us is the standard deviation of 1 minus x is still the standard deviation of x. So that's going to be 120. And that means the variance of 1 minus x is 14,400. Why? Because it's 120 squared. Okay? So now I'm going to play 5 times. Okay? Well, what's going to be the mean of these 5 times that I play? Well, the mean is going to be the mean of one time plus the mean of the next time plus the mean of the next time. So basically, it's just going to be 5 times 0.08, which is 40 cents. Okay? We're expecting to make 40 cents for somebody playing 5 times. In order to calculate the standard deviation, let's calculate the variance first. So the variance is going to be, remember what happens when you have, what's happening here when we play 5 times, it's a random variable plus a random variable plus a random variable plus a random variable, and each of those random variables has exactly the same distribution. So what we're going to do is take this variance and add it up 5 times. So that gives us 14,400 times 5, which is 72,000. What's the standard deviation? The square root of the variance. And that equals about 268.33 dollars. The mean and standard deviation are in the same units. The variance is in, I guess it would be in square dollars, but I don't really understand what that means. So, if gamblers play this machine 1,000 times in a day, what are the mean and standard deviation of the casino's profit? We do the exact same thing, except instead of multiplying times 5, we multiply times 1,000. So the mean is going to be 0.08 times 1,000, which I believe comes out to 80. And the variance is going to be 14,400 times 1,000, which is 14,400,000. Okay? And our standard deviation is the square root of the variance. So I take my 14,400,000 and take that, the square root of that, and I'm getting 3794.73. So $3,794.73. Okay. Do you think the casino is likely to be profitable? I think it will. Because people play these slot machines like crazy. If they play 1,000 times in a day, you're making $80 a day. I'm expecting that it's going to be profitable. Okay? Is it definitely going to be profitable? No. Because there's variation. Okay? Sometimes you lose, sometimes you win. If people hit a whole bunch of jackpots in a row, if each pull of the lever is absolutely independent with the others, then, well, you might actually lose money every once in a while. But over the long haul, yes, it will definitely be profitable. Okay? And then finally, why is the standard deviation so large in comparison to the mean? Well, remember, standard deviation, when you're talking about data, it's measuring how spread out the data values are. When you're talking about random variables, it's measuring how volatile that random variable is, which is kind of the same thing as the spread. It could be something over here, it could be something way over here. Well, in this particular case, the payout is either 0 or something pretty big. Granted, the probability of something pretty big is small, but still, that gives you a large standard deviation. And that is our last problem that we're doing, so I hope this has helped.